Hi, everyone. I'm Yousif Hussin. Welcome to NDC London. Can you hear me clearly? Okay, great. I'm Yousif Hussin. I'm a security engineer at Google. I've been a security engineer for quite a while. I started in like 2007. I don't know if some of you from America maybe, you know the company called TiVo. Back in the days, it was a big thing, but not anymore. So that's when I started my internship in security. And I was like, OK, I think I really like this. But before that, I've always been passionate about security, more specifically hacking and just breaking things. I was just very, very curious on how to make things, do things they're not expected to do. And that's kind of how I got into really security. And I do believe that if you want to really protect the system, you really need to know how to break it. That's probably about the best way you can start doing that. And before Google, I also worked a little bit with Apple, Microsoft, and Meta. And in the past, like maybe 9 years, I've been focusing more on what do we do when we get bad news? Like, okay, like kind of news like, hey, Yousif, wake up, we got hacked. What do we do? Kind of stuff. Sometimes it's like malware. Sometimes I have to do forensics and different sorts of things. It's always been fun for me because it's kind of like solving a puzzle. Like, hey, computer, like this big infrastructure of computers that got hacked or has a malware infection. What do we do about it in a very short time frame and minimizing the cost of addressing the problem? And it's always been very, very interesting. Although in the first few times I did this, I was kind of panicking, but then I kind of got used to it. And then it's like solving a puzzle. OK, how do we get all these logs, all these system artifacts, and how can we paint a picture of what actually happened, and what do we do about it in the future? So very recently, I switched teams within Google. And now I'm part of a team called the Infrastructure Protection Team. It's the team that's responsible for building security controls for Google's infrastructure. And so my role is like security engineer / software engineer / SRE sometimes. And one of the things that is very common at Google is if you're a security engineer, you're also a developer, you're expected to read and write code. And it's one of the things that we like to do is reading and writing code and identifying bugs in code, and also writing code for automation for security teams. So before I joined this new team, I was actually part of another team called the Vulnerability Coordination Center. And this talk is relevant to that role that I had before. And basically, I was straddling two teams. The first team is the Vulnerability Coordination Center. And the second team is something you might be familiar with externally, the Bug Bounty program for Google. Like if we report a security problem to Google, Google Cloud or any product at Google, it will come to this team, and I would triage it. Like if you ever submitted something and you got a response that says, hey, it's a bad report or it's duplicate, it might have been me. So that's the kind of stuff I was doing. But at the same time, I'm part of the other team, Vulnerability Coordination Center, and this team is a little bit interesting. What this team does is, OK, let's say we've got a vulnerability, but it's really, really complex, something pretty big. It has a massive impact and also involves a lot of teams to fix this vulnerability. So it's not just, oh, let's just patch that Windows system or Linux system and we're done. It's a lot more work. And we have to do it within a short time frame. So that's why we have this team at Google that is dedicated to that mission. We've got something big. How do we orchestrate the remediation to this big vulnerability-related problem? Because at Google, when you find a vulnerability, that is already a problem. I know traditionally in other like generally in my experience before Google, an incident is when you get a malware infection or you get hacked or something like that. You declare an incident and then you manage that incident. At Google, once you identify a vulnerability, we're not even hacked yet. That's already an incident, and then we manage it like it is a big incident. Because once that happens, you're kind of fighting against time because somebody knows this vulnerability. How long is it going to take for other people to know about it? And then basically use it against you, even if it was discovered internally at Google. So sometime when I work in this team, the Bug Hunter Bounty program, I would receive bugs about security that people report to Google. I found a way to, I don't know, like to break into the system through SQL injection or cross-site scripting or something like that. And then I would work with the developers on how to address that vulnerability. Sometimes it's something big. And this queue is not only external facing, also internal Googlers facing. We have security researchers at Google that find problems too. A lot of problems, a lot of very interesting problems. So sometimes when I get something here, and then I'll be like, okay, this actually needs a little bit more work, I'm going to escalate it to the Vulnerability Coordination Center. And then the next morning, I would probably be like in this other team. I'm looking at the queue, and I'm like, I see this escalation from myself over there, and then I would actually lead the response to that particular remediation for that particular vulnerability. So VulCC is the short name for the team, Vulnerability Coordination Center. It's a team of security professionals who specialize in vulnerability remediation and also know how to manage teams at scale. And how do we do that? I'm going to go through some of the details of this. When I joined Google and I joined this team, initially I was like, yeah, I've always been wanting to join Google, but I always got rejected. I worked at this other company, and then once I got into this team, and I was like, this is really interesting stuff. We deal with these big vulnerabilities and stuff. Like, I have no idea how we're going to do that, how I'm going to do this, but I'm really interested in getting into this kind of stuff. I really want to play in this. And then I saw my teammates dealing with big vulnerabilities across Google. How do we remediate this problem at scale? And I was like, I really want to do one of these. But it took a while. I was like shadowing. I was like learning from others. I was like, I want to do one of these. And I started complaining. But then later on, things changed. And this is basically the story I'm going to go through this in this talk. Yeah. Sorry, just hold on. Okay, anyway, so I need to build a little bit of context so that we're all on the same track. So I have to do a little bit of homework just to make sure that I don't say something that doesn't make sense. First of all, just a quick question. If you look at this set of bits, how many of you can actually look at this and tell me what this is? Like, oh, this is a hello program or something like that. Raise your hand if you can. Oh, that's expected. I would jump if somebody raised your hand. It's expected. I mean, not a lot. But as some of you might know, is that sometimes we have to read computer code, but in different ways, right? Different level, different layers, different abstractions. And if you really want to read something like this, there's one way you can do that by stepping a little bit back in a disassembler, and you can actually see the representation of those machine instructions in something called assembly, right? So you could see the machine instructions. And even assembly itself isn't something that everybody reads, right? Like every day, right? And some researchers do. When I used to work with malware, I also used to see a little bit of assembly to understand what the malware does. But it's not something very common. So this talk is not actually going to show a lot of code like C++ or anything like that. Should be light. I know it's like kind of before lunch, so I want to make sure that you go to lunch, happy and looking forward to it. But just a little bit of a lie. There is a little bit of code, but to make it even worse, it's assembly, but it's not going to be that much. But so this is a machine instruction. So as it turns out, when you write a program and you compile it, and you give it to the machine to run it, it goes all the way down to the machines, and it translates to a set of machine instructions. And what the machine does, it actually just moving things around, moving bits around in this machine, little objects called registers, right? Like moving bits around and then doing some computations. And moving things between registers is important for the machine to be doing these computations. And to do this, it would have to be able to understand which register I need to get a bit from and which register I need to move a bit from. So for example, this machine instruction basically says move, which is really moving something. And EAX, EBX is really just the names of the registers you're moving things from and to. So this basically does this. It says move from here to there. Don't ask me why. It's like move and then doing this. And I'm sure these people are really brilliant who came up with this, but sometimes I just don't understand why they came up with these ways of doing things. But that's the way it is. You're actually moving something from this register called EBX to another register called EAX. That's really what the machine is doing. That's pretty much it. Very simple. But then you've got another machine instruction called MoveSB. MoveSB is another assembly instruction that actually also moves some bits from a register to another. But here you don't see operands. You don't see like source and destination, right? And the reason for this is that because it's implicit. The machine knows when you use this instruction where it's going to move something from and to. It's like it knows that there's a destination. It already does a little bit of work that looks like this. And then you see rep before it, and in machine instruction, rep basically means repeat. Just do the instruction again. So this is repeat the instruction. Can anybody tell me what happens if you give the machine an instruction to do this? Repeat, repeat, and then the instruction. Would this break it? Would this cause an issue? Okay. As it turns out, it doesn't do anything. Basically, the machine ignores it, and it works even if you do this. It's fine. It's just going to move something from here to there, and it's absolutely OK. So that's concept one. The two more things I'm going to go through very, very quickly before I get into the story. Intel CPUs, like not too long ago, introduced a feature called ERMS. I was just talking about moving things in the machines, right? So they thought, OK, well, there is a way we could actually make these moves a little bit more efficient. So they introduced a feature called ERMS, which is short for Enhanced Repeat Move Store. And basically what it does is make these moves a little bit more efficient. But to do this, it will do a little bit of work before, and then it will do the move. Sometimes if the data you're moving or the bits you're moving are like just so little, if it's not a lot of data, then it's really not worth the investment because the pre-work is actually a little bit more than the data you're moving. So it's like, maybe I shouldn't do it. And that's why they had another feature called FSRM, which is short for Fast, Short, Repeat, Move. These are probably some of the most difficult tech names I've ever come across. Like, I'm pretty sure these guys are very smart, but I really don't know what they were thinking when they came up with this. Like, I'm pretty sure it could have been a little bit simpler. But anyway, these are the two features. FSRM basically addresses the problem with small set of bits that you're moving that I just mentioned earlier with the RMS. So remember this. There's a feature called FSRM. It's for efficiency. It's introduced in Intel. So in 32-bit machines, we've got 8 registers, right? And this machine instruction says move from EBX to EAX. EBX, EAX, these are like 3-bit size location, which basically means you can address like how many registers? 8, right? 3 bits. So that's in 32-bit machines. So that's enough. But now, when we got 64-bit machines, we've got 16 registers. What are we going to do? How are we going to be able to address them with 3 bits? And they were like, well, one way we could do it is we could just hack it a little bit, and we just keep it like 32-bit instructions. But then remember when I said earlier, you could actually add something that gets ignored by the machine? How about we add this kind of prefix and give it a name called rex register extension? And then we use it to borrow a bit to the location. That way we have 4 bits, and now we can address 16 registers in the machine. So that's what they did, basically. Now, the last concept I want to touch before I move on to the story, does anybody know what this is? What this logo represents? Okay, that's okay. So I assure you that everybody in this room knows this a little bit. And I'll get back to this later. So the response to story. So I said earlier that I was complaining, okay, I really wanted to lead one of these big responses to vulnerabilities at Google. And then one day, this changed, and I actually got to deal with something really, really interesting. What happened was some of the researchers at Google, they fuzz the programs in the machines, basically identify security problems. So what they do, sometimes they do it, get one copy of a program, get another copy of the same program that produces the same output, and then we'll change some of the characteristics of this program, and then run them, and then change the characteristics and run them. And then if one of the programs behaves a little bit differently than the other, and that kind of suggests there is something weird in the program, and it could be a security problem. So what they did was they were like, okay, well, we're going to add the register extension that I mentioned earlier. How about we also introduce the feature of FSRM? With certain conditions, this led to this. What I mean by this is machine check exception. You crash the machine. And this is basically was what the vulnerability that they identified was. It's called Reptar now. So So this is it. So this is something that was like, I came to VulnCC, Vulnerability Coordination Center, and I was like, hey, Yousif, okay, you've been asking for stuff like this. How about you go and delete this? I was like, CPU? I mean, I was complaining, but maybe something a little bit higher level. But yeah, so I was excited about it, and then I was like, okay, I'm going to lead this response. I'm going to address this problem at scale at Google, and then see what we do. But then the other challenge about this is that it doesn't only affect Google. It's Intel CPUs. The impact was pretty massive. So the response looks like this. And it's a little bit, it's fun. Maybe not as fun as playing Super Mario, but that's kind of just the way I like to represent it. But we're going to be starting from here all the way to the end. And what I mean by response embargo period is that once we identify a vulnerability like this, we have to report it to the vendor. And in this case, it was Intel. We reported to Intel, and this basically starts what we call an embargo period, about 3 months. And in this period, we have to sort things out. Normally what we do is we start with something called the impact assessment. This is like the first step. And what the impact assessment is really just, you know what it is, but at Google we have a very, very specific streamlined process around what impact assessment is. And we have to answer questions like, how easy is it to exploit the vulnerability? What kind of systems are they impact at Google? What kind of systems are they impact outside of Google? And is it really exploitable internally or only externally? Things like that. So now we understand that this particular vulnerability, all it does is you would run instructions on a machine and would crash it, right? So it looks like this. Okay, let's say that you're on a machine. You run the machine instructions for this particular exploit. You run the exploit, you crash the machine. No big deal, right? Like, okay, you crash a machine. So I'm going to say something. I don't know, but feel free to correct me if you agree. But it's not really a big deal, is it? Because you've got your own machine, you've got instructions, you run it, you crash the machine. It's your own machine. You're kind of like you're hurting yourself. Like, is that really a problem? If it's a problem, raise your hand. If it's not a problem at all, raise your hand. Okay, all right. I'm glad that you agree. Okay, so let's take another example. Let's say this machine, like my cousin said, okay, me and my brother, we couldn't really afford any machines, so we wanted to basically share machines. And then my cousin was like, okay, I'm going to give you your machines, or you're going to have to pay for it, you and your brother, I don't know, $5 a week or something. And then we shared this machine. Okay, we've got virtual machines. Machine for myself, my brother, and my sister. And then I run the exploit. Turns out that the same happens. Close. So basically, it crashes the underlying machine. It's not just my own host. It's the underlying the underlying physical machines. So maybe you've already seen the slide, but can you think of a product or something that could be affected by this? Or maybe at massive scale?
Anything on the cloud.
Anything on the cloud? Mm-hmm. Exactly, anything on the cloud. Yeah, but when you think about like something pretty problematic, like in today's world, you think cloud providers, and because I was working at Google, I was thinking Google Cloud, and yes, that was the first one. So at Google Cloud, you can basically just as simple as go and open up a virtual machine, which is really easy, right? Anybody can do it for free, and you can just go and you just run instructions, and you would crash the physical machine, which you don't know who you're sharing it with, right? And that's a bit of a problem. So we thought, okay, well, that's already kind of big, because it's not just about crashing your machine. Crashing your machine, you're actually crashing other people's machines, and it could be mission-critical applications running on those machines on Google Cloud. So it looks a little bit like this. It's pretty simple. You got your own machine, you run the exploit, you crash the host, and as a consequence of that, you would crash the other virtual machines running on that host. I mentioned earlier, what is this logo? So about a little bit of history. About 20 years ago, 2003, a little bit more than 20 years ago, at Google, we wanted to manage our machines in our data centers globally more efficiently. So not in the traditional way of, okay, you've got a workload that you want to run, you allocate the machine, and then you run that workload on it. That wouldn't work anymore at scale. So we wanted to basically use the machines more efficiently. So what we did was we had a system that would help automate the provisioning of these machines globally, and also centralized management of these machines globally in our data centers. And then a couple of years later, we also wanted to improve the scale of this. We wanted to even build on top of this system and make it even better. And we wanted to share these machines across Google. And that's when the developers at Google came up with C groups, control groups. If you're familiar with it, the Linux kernel feature, in which you can basically isolate workloads so they don't step on each other's resources. And that basically was Borg. So this logo was for something called Borg that we use at Google, which is really just a cluster management system for Google's infrastructure globally. All of our data centers, all of our software that we run on Borg. And then we thought, okay, we could maintain Borg and we could use it because it just scales and it works very well with Google's internal tooling in the future. And we could just basically make it better with time. And we use it to manage our clusters in all of our data centers globally. And then later on, about maybe 10 years later or something like that, this basically inspired the creation of something that became public. Can anybody tell me what that is? Kubernetes. Yeah, Kubernetes, basically. So this is really how we got to Kubernetes anyway. So now that you understand what Borg is, and by the way, we use Borg today at Google. Now we understand what Borg is and the way that it works. Do you think it would be maybe affected by something like this as well? Like, yeah, right, because it's kind of in the same fashion as in cloud, like it's like we're sharing machines. So yes, we had Borg machines that run Intel CPUs, so they were affected by the vulnerability as well. So that was part of the impact assessment. Okay, well, it turns out that it's not just cloud, but also Google's infrastructure running on Borg is affected by this vulnerability. So, okay, that's kind of escalates things a little bit more. Okay, here's the question. Is that all? Can you think of something that might be affected? And it's not necessarily something esoteric to Google. So I've been talking about servers. Do you think clients would be affected? Like, do we ever have clients that run Intel CPUs? Yeah. So as far as Google is concerned, we've got Chrome OS devices. And these were affected. But also there are non-Chrome OS devices that are affected because they're running Intel CPUs. But do you really think it's a problem? Like, okay, well, when it comes to client, it's not like you're sharing your client laptop with people like in the cloud and things like that. And we always get crashes. You just reboot your machine. You just restart your machine, right? Like right now I'm doing this presentation. I'm so happy I'm doing it on a Mac OS. But if it was like some other operating system and it just updates, like it will just restart, right? It gets me in trouble. And we got used to this, right? Like it's not like something super new. So yeah, so this guy again is like saying, oh, bro, it's not a big deal. It's just your client, you just reboot it. It's really not going to affect anyone. So a little bit later throughout this remediation effort, Intel was doing their own research internally. So when we identified this vulnerability, Intel CPU is a black box for us. We don't actually get to see all of the internals. We drop things at it, and it acts weird, and we found the problem. But then Intel knows the internals of it. So what happens was that Intel came back, and they said, whoops, turns out that through the vulnerability, you can actually do privilege escalation. So yes. So this is how it looks like for us. It's black box. That's what I was trying to present here. But then they can actually see inside. And then they said, well, we can actually do a little bit more. Privilege escalation. So now, just for those of you who don't know what privilege escalation is, it's like, okay, you get into the machine with like normal user, and then you manage to go up to like admin or root. So you basically own the machine, right? So that's a little bit of a problem, right? Not only for pretty much everything. Like even if you go back to servers, I was just talking to servers, that's a bit of a problem. You're not just crashing now anymore. You're basically owning the machine, right? And then when you're talking about clients, does that change anything? It changes things a lot, right? Like, okay, so we're not really crashing clients. And then here is a question, like raise your hand if you've done it or if you've come across it or if you've researched it. But do you think it's possible to exploit something like this through a browsing session? Maybe. I like that answer. So in theory, it's possible. I personally haven't seen someone recently doing like, hey, here you go, exploit. In theory, it's possible though. But again, as far as we're concerned, we have to assume that it is possible and go with that. So now we've got servers, you get to privilege escalation, we know that, and then with clients, it's the same thing. And for Google's impacted products, we've got Google Cloud, we've got our internal work, and then also got Chrome OS. So what we do as part of the impact assessment is that, okay, when we get to that point, we understand the vulnerability, we know the impact, we know how bad it is, but we really need to count how many machines are impacted, because we've really got like, I don't know, maybe like a month and a half now at this point, and we really need to kind of fix this. So what we do is at Google, once you identify the platform and the CPU families that you have, it's actually pretty easy to find out how many machines are actually impacted. So you've got Google Cloud, and then it's really just like a set of SQL statements that we run in our discovery systems. And then we'll tell it, okay, Google Cloud, Chrome OS, for Borg, how many do we have that run Intel, these kind of CPU families, and then we get these kind of aggregate numbers. And now we know how many we've got. But how do we fix this? This was a very important question. Like, okay, we've been talking about machines, and now we know the numbers, but I mean, if we're going to be pushing something to these machines, it's got to be a fix that works. But right now, we really haven't talked about that. So one way we can address this is we could just wait for the vendor. Like, let's say that we've got like about a month now, and we've already reported it to Intel, and then we can wait for the vendor to report it. But then is there a problem with that? Like, can anybody think of an issue with waiting for the vendor? Even assuming that they're going to come back to us before the embargo period. Do you think there might be the risk of a leak of this vulnerability gets known, and then we get hacked or something, or somebody else gets hacked? So we could wait. So that's one way we could address this. But the other option was we could actually also come up with our own solution. So while we were actually working on this remediation effort, I had a team that actually looks into what can we do internally at Google that might remediate this problem. Let's assume that the vendor is not going to come back to us with a fix. And then one of the engineers came up with an idea. Can anybody tell me what this is? If you're familiar with like CPUs and some of the ways you could disable things. Okay. Yes, exactly. It's chicken bit. I think this is the first time I actually did this talk and somebody actually knew it. But anyway, good. So as it turns out, in the CPU, sometimes they introduce a feature, and they introduce also a bit that comes with the CPU that you can flip to disable that feature. They called it the chicken bit. I think they called it the chicken bit because you have the option to chicken out of the feature, like, ooh, I'm scared, I don't know. But so what the engineers said, well, that feature, FSRM, that we talked about earlier, was a prerequisite for this to be exploitable. How about we just disable it with the chicken bit? And that works. We tested it, and it works. But can somebody tell me why this could be a problem? What? It will break everybody's code? You're close to it. So FSRM, what kind of feature was it? It was a performance feature. So when we disable it, what's going to happen? Yeah, performance is going to go down, right? So we tested it, and we tried to measure the impact in terms of performance. It was like 10%, which is big, but not like the machine is going to stop. So we thought it would be a good idea to keep it in our back pocket. And if we don't get something from a vendor, and then let's assume that worst case scenario gets leaked, maybe it's better to go down performance 10% than get hacked altogether, right? So we could have that option. So that's what we did. We just kept it there. Okay, that's an option that we can remediate this probability, but let's wait a little bit more. Good news is that we did actually get a firmware update from Intel to address this vulnerability. And we had a period of a few weeks to test this in production. And then we can tell Intel, okay, this works. And not only us, there's like a circle of big companies that are also involved in this, similar large companies, like some other cloud providers as well. So we had the multiple solutions now that I just mentioned. We've got like the chicken bit, and then we've got the firmware update that we got from Intel. As you can see here, they all work, they're all effective, but then we've got the performance hit with the chicken bit, and then we've got the effective solution without the performance hit, which is the firmware update, microcode update. And for client, things are a little bit different than it is for servers. For clients, actually pretty easy, because once you have the update, you would have it online, and then people will basically just pull it, and they'll update. But for servers, things get a little bit messy. So now we've got a solution, we've got a fix. How are we going to roll it out to these servers? Are we just going to be like rebooting the machines? Yeah, I mean, that's an option, right? I mean, we could do that if we want to, but I think, well, we're just talking about performance. Like, okay, we don't want to go down 10%, but then if you reboot the machines and make an update, like a BIOS update, like that's I don't know, like the machine is going to go down 0, I guess, like for a few seconds, and that could be a problem. So there is a couple of strategies on how you can roll out a firmware update like this to the CPUs. And one of them, like I said, is the BIOS update that you can basically reboot the machines and you can apply it. But can somebody think of, for those who might have done this, or of a way you could actually apply a fix like this without rebooting the machines? Okay, so there's a method called hot loading the firmware, which is basically just updating the CPU firmware without having to reboot it. In the public domain, people get a little bit concerned when we talk about this. It's like, oh, this could cause issues. No, it's not proper and stuff. But anyway, we've done proper testing internally, and we've actually rolled out the fix to all of our server fleet, like Borg and also Google Cloud, transparently, without touching any customer workload. And it was pretty effective. Now, when I say transparently, is it really 100% transparently? Like, no. But it doesn't really have an effect on the application that runs on top of these machines. Like, if you're really gonna go down to like the CPU cycles and monitor it, you're probably gonna see a difference, right? Something called a brownout at Google. But it's not really something that's going to affect the performance of the application. In that way, we can say it's transparent. So we did hot load it. And then when it comes to the, at that point, we got to like just before November, and we rolled out the, we prepared the client update. And then we wanted to make sure that everything is fixed. One of the interesting discussions we had was we wanted to make sure that this is really, really locked down properly. And only a few people that are involved in this response know about this. And to the point, one time we were talking about, what if we give this to the server engineer, and then they get the patch and they update it? Maybe there's like a side effect through which they can actually identify the problem and then know the vulnerability and things like that. It's a little bit of fantasy, but we had these kind of discussions. But in practice, this isn't really a concern you'd see every day. It's not very common that somebody would be like, oh, I'm applying a patch, I'm actually going to reverse engineer the patch to identify the vulnerability, and now I can build an exploit before the embargo period and sell it in the black market or whatever. It's not like, it's possible, but it's not easy. So now I've talked about all of these things that we've done, but how do we do this at Google? We just do it randomly. So we've got like a set of protocols that we follow at Google. We've got something called IMAG, which is short for Incident Management at Google. IMAG is really just a program of managing incidents effectively, and it gives you like guidance as to how you can build the communication channels, how you can build the team for the response, what kind of protocols do you follow, and how do you manage the incident end to end without panicking and causing problems. This is basically inspired by protocols that are followed by the medics and firefighters. It's because if you think about it, it's pretty much the same problem. Right? You just want to follow a playbook when you're in the middle of an incident like this. And this is what we did also for this response. So we had initially, when I started this response, I had to build a team that's going to be dedicated to this response. And at Google, when you do this, when you follow the IMAC protocol, once you are the incident commander, it's kind of like you're the CEO for that. It's kind of like, doesn't really follow the organizational structure anymore. You're at the top of this. But you're ultimately responsible for it. I remember when I joined Google, I had a training for IMAC, and they said this is the only time you can boss your own boss. You're ultimately responsible, but you're at the top of this. So this is the team. Me, incident commander. I wish, right? Like, it's not really like that. Like, you couldn't just click buttons and be like, okay, get things done. But I had to think about what kind of team do I need to execute on this response effectively. And here's how the team looks like. Initially, I started with something called the operations lead. It's basically the person that I was telling, hey, we need to get this fixed. This is the first thing we need to do. We need to get this fixed. Let's try to identify a fix and how we're going to be rolling this fix immediately. So that was the operations lead, which I think was the most important role under the incident commander. And then the operations lead was like, oh, well, there's a lot of work here. So we're going to have another lead that's going to be leading data center. And then on the data center, we had another lead that's going to be leading Google Cloud. Same thing goes for like client, Chrome OS, Chrome lead, response lead, Chrome OS response lead. And then for the internal Google infrastructure, we also had our enterprise systems. So we had a lead that's actually going to look into securing that part. So that's corporate systems response lead. And then we've got the platform security lead who supports the corporate system response lead. Tech research lead, why do we need that? So this is the lead that actually leads the team that identified the vulnerability, but at the same time, they help with other things. Like, for example, how do we detect it? Is there any way we can look for indications in Google infrastructure that this has been exploited in the past, and things like that? So we really needed to do a little bit of work like that with them as well. And then we've got the tech lead who also does a lot of work for the response in terms of the technical side, but also the engagement with Intel. Communications lead, of course, there's a lot of like communication things that we have to do. Like, for example, how do we communicate this to customers, internally, externally? How do we communicate this to other Googlers that are going to be involved in this? How are we going to be talking to Google Cloud customers and tell them about this, for example? And then at the end, there is also another lead that leads this green bubble, which is non-Google alphabets response lead. Can anybody tell me what that means? What is a non-Google alphabet? If you're familiar with that, okay. Yes. Yeah. So Alphabet is the parent company, and then under it, it's not just Google, right? So we've got other things like, for example, I don't know, self-driving cars, Waymo, and Verily, and some of the other stuff. So these are other companies that we also have to protect. Interestingly, Google only had the NDA with Intel directly, and that wouldn't involve the other alphabet, non-Google alphabet companies. So we actually couldn't do much when it comes to the non-Google alphabet companies until this was published, so that we could fix the non-Google alphabet companies with everybody else. But before publishing, we had to fix everything inside Google. So this is what the team really looks like. And these are only the leads. These are not only the individuals that are working on this. For each lead, there's like a team that supports. So this is kind of just give you an idea of the kind of complexity that goes into this. So we got to the point where we had to do the final step, which is kind of like a celebration kind of step, celebratory step, which is really just telling everybody about this. Like, okay, hey, we've published this vulnerability, everybody knows about this, and here's the fix, and here's how you can identify the vulnerability and things like that, and then the public domain knows about it, and then I can, as an incident commander, can also say, okay, I'm done with this work, which is disclosure. There's something called the security bulletin that we publish, which basically stipulates the details of the vulnerability. And that's what we did, the disclosure date. And then around December, we're like, okay, we're done. Now we can celebrate and we can basically take holiday. And I was like about just to take my holiday. I was like, okay, that's good. That was fun, but you need to chillax a little bit. Now, here's the question. There is something called Cloud Shell. Anybody knows about it? Okay, it's like an interactive environment in Google Cloud, that interactive shell environment in Google Cloud. You can actually go and have like a shell environment in Google Cloud, and you can interact with it, run command in shell. And then what happened was after all of this, and after we've published the vulnerability and everything and we're done, we got this message from the public domain from someone. I just heard about Reptar. So Icebreak is a tool that we published that will tell you if your system is vulnerable to this or not. And Cloud Shell is the interactive shell environment. Somebody said, I just heard about Reptar. I tried running this Icebreak tool that you guys gave to us publicly on Cloud Shell, and it worked. And I was like, yeah, I was just about to go on holidays. It doesn't seem like it. After all of this work, so we haven't really fixed anything. So we kind of panicked a little bit for like half a day. And then when we looked into this a little bit more with the researchers and everything and looking into the servers and trying to make sure things are fixed, turns out that the Icebreak tool had a bug in it. And so he was lying. It's not like the fix didn't apply or anything like that. So anyway, so that was really kind of like the journey that we went through. And what did we learn from this? Some of the things that I feel like were really, really important was having this IMAC protocol as part of this program, because there are a lot of decisions that we had to make in the middle that were really important. And there were a lot of times we were like kind of prone to panic. And having this kind of protocol and playbooks was really, really important. And I always advise my team afterward that just follow the IMAC protocol. And here is an IMAC structure for CPU type responses that I created for this response. Just follow that. What can we do better? Some of the things we can do better was automation. So we did a lot of work manually, and I think we can automate a little bit of the work. And that actually led to a project that I worked on after. Can we automate? Of course. Can we automate? We already automate, but we could automate a little bit more. Are we prepared for the next one? I do believe that Google is very, very prepared for the next one in terms of like the team capabilities and skill set and also the infrastructure that we have. We just have to make sure that we religiously follow the IMAC protocol and do this properly. One of the things that I worked on after was something called Google's CPU response toolkit. It's something that I built, which is really what it does is it will automate the bootstrapping of the response and the creation of the response artifacts and set of tools that you would use as an incident commander to run that response. So this is an automation that I built that will do this for the incident responder so that the incident responder will only focus on the analytical areas that need some human to really intervene and make certain decisions. So it would create things like, here are the communication artifacts. Here is like the draft of the fix. Here are the teams that you're supposed to involve in this. And now all you have to do is just focus on the things that you really want to focus on as an incident commander now to get this done very, very quickly and effectively. And that's it. I delivered this project recently, and it's being used by Google quite frequently. If you would like to connect with me, I'm more than happy to connect on LinkedIn. This is my name. Feel free to reach out to me if you have any questions or if you want to know a little bit more about this. And if you want to send me an email, also this is my email. So actually, I think it's easy. And yeah, I hope you got a little bit of a glimpse of how we manage vulnerability-related incidents at Google and that it was useful. For reasons, I would appreciate if we don't do questions here. But I'm more than happy to answer any questions like during lunch or outside. You can reach out to me, and I prefer that kind of interaction and questions instead of doing it here on camera. Okay, thank you.